На видеоискателе.
Нет.
Что?
Видеоискатель.
Зеркальный аппарат. Зеркало. Он отражает сюда. Я понял, что я ничего не понимаю.
Максим, смотри дырочку и нажимаем
Объектив открыт. Объектив. Ну раз нет, то... Хорошо.
Как можно узнать, что он сфотографировал?
Она появится. Okay, so what I want to tell you, it's kind of more philosophical discussion. So there is a general idea of randomness and probability, and I'll try to explain some extension of this. So, but let me start with just to show the parallelism. So what we do, for example, what we do usually, we have a fair coin, and we make an experiment, and so we have a probability distribution, which is uniform distribution on the set of all outcomes, and then we see, for example, then some outcome for, like alternating zeros and one happens, and then we say that it has small probability, and so then we reject our assumption that the coin is fair. So this is a very general scheme. We make some assumption about probability distribution. We have some experiment. We see the outcome, and we know something very which has very small probability happens, and so we decided our assumption was not...
Every exact outcome has very small probability.
Yeah.
Is this the check? Are we sleeping?
Yeah, it's a classical paradox with this, and it has many answers. One probably real experts will tell you that you should specify the outcome before the experiment. If you, after the experiment, say that, look, we happen exactly this has small probability, it's not convincing. So that's a classical answer. A more algorithmic way of saying more or less the same is that when you find a simple string which has small probability, then you are done. It's bad. If you have if you have a string which has high complexity, then its appearance doesn't mean anything. So, but this is classical setting. But what I want to say that actually we often use probability theory or just similar arguments in some cases when this is not we cannot do this. For example, imagine that these coin tosses are made, probably before when you play chess, in a chess championship, there is a coin tossing before each game to decide who will start. So imagine there is a special referee who produces coin tossing. And now there is, for example, some player want to complain that the referee is not good, that he's really cheating. So what kind of complaints could be here? So for example, if all the coins are zeros, then probably the committee will agree with the complaint. But there are more delicate things. For example, there are also some games before something happens in between the coin tosses. So imagine that the result of these coin tosses can be predicted by a simple rule based on the previous game. Then probably you will say that the referee is not fair, yeah?
First you have to discover this rule.
Yeah, but imagine that somebody created, look, here is the rule, and here is I give you the protocol, and you see that the rule is really simple, and it's indeed always the case. And so being in the disciplinary committee of the tournament, Probably you will agree with this.
It's more or less the same paradox. I mean, if he does it afterwards, then we could argue that he specifically looked
Yeah,
at
okay,
the
but imagine that the complaint was somebody told you that, look, I know this referee is not good, but I'll prove this. I'll predict that this will be this or that, computed by this rule, and you see that this is the case, and then probably you will say that the referee is bad.
We played some trillion of parties. Well, it's not realistic, but anyway, and the rule can be stated in 100 letters. It is suspicious. Anyway, even afterwards.
No, but look, if the rule is for all the parties, for all the games, or for some fragment.
If the rule is for all the games.
No, but okay, but actually, what I want to say is completely orthogonal to this. So this is a paradox which can be discussed for centuries, and there are huge books in probabilists wrote huge books about what is probability, is it observable, or it's our belief, or it's objective, and you never can understand what is there. But I would say a very simple thing. But so you agree that, for example, if there is a rule which computes this from that, it will be a bad thing. But now, let me ask another question. Imagine there is a rule that can compute this bit looking at this thing, and the result of the next game.
Wow.
Will it be suspicious or not?
It means that one has significant bonus.
Yeah. So this could be quite easily explained without any cheating, because who knows? Maybe the result of the game, the result of the coin tossing has a heavy influence. Maybe the Grossmeister knows that if the coin has a tail, it's a bad sign. He is disappointed and he cannot play well, and so on.
Yeah, maybe the referee just decides who plays white and who has plays black in chess.
Or maybe that's very important for chess also. Or a similar example. So if you imagine there is a lottery, as a result of a lottery, and this is newspapers. So if you can predict the result of the lottery reading the newspaper from the day before, it's very bad for the lottery organizers. But if you can predict the result of the lottery looking at the newspapers after, there is nothing bad. Maybe they just print the result. So, but what I want to stress, that in probability theory, can you explain why one thing is bad and other thing is good, just in terms of probability theory?
Hardly. It's just a correlation.
Correlation between what?
Between these two events. So, well, you can't really distinguish unless you have a notion of time or a sequence of events.
Yeah, of course you know the sequence of events, but what is the difference between two cases? And so the problem is actually that what makes this setting not why we cannot say that it's a good thing in classical probability theory, because there is no we have some probability assumption about the bits, that they are really fair coin. But of course we do not have any assumptions about the newspapers or about the games. So we cannot apply classical probability theory because we don't have any distribution at all. So what we have is some other object. And it seems that only recently different people under different names started to consider. Maybe, in my opinion, it's quite possible that, I don't know, Pascal or Fermat or Kolmogorov or whoever already should consider this. But I didn't find any traces of this. So the idea is we have some interchanging stages. Sometimes there is a choice made by environment without any probability. Like here, the newspaper. We don't know anything about distribution of newspapers. And then there is something which has a clear probabilistic assumption. For example, we toss a coin. So there are conditional, so to say, we have a conditional distribution. So for all in each vertex, we have the probabilities of the next step. And then we have the, again, the choice made by environment. And we have we go to some level. And now we can consider two events. So events are just subset of the set of leaves. So so the event is that bit number Ci is a function of previous, so it's x1, C1, x2, C2. So the event Ci is f of xi. For example, for all I. So still, there is some feeling that the probability of this is 1 over 2 to the n. And if we say that the event, if we have a different event, that Ci is f of xi plus 1, then we cannot say that the probability is 1 over 2 to the n, intuitively. And so, the question, what is the formal definition? So we have this framework. We have the tree, and we have probability distributions on different paths on each level number 2, number 4, and so on. So what is the correct formal definition? What quantities here are 1 over 2 to the n, and here is unknown? Can you explain the difference? So this is exactly the question, in my opinion, why one thing is strange and other is allowed. So what is the notion of probability which is appropriate for here?
Conditional probability.
But usually conditional probability in classical setting is just a fraction. And now we don't have...
but we don't know neither the denominator nor...
Yeah, we don't... The question is not defined.
Yeah.
So, but still, for somehow intuitively, we can say that this has probability 1 over 2 to the n.
I understood that he explained that instead of probability distribution, we have just conditional probability distributions in each node, right?
Yeah. Like in Bayesian networks.
In each node, we have conditional probability distribution.
Yeah, so we have a conditional probability distribution of the event to come here with the condition we are already here.
Yes.
Yeah, but what do you mean by conditional distribution? By usually classical...
A set of conditional probabilities.
No. So a set of numbers which you call conditional probabilities, which are not conditional probabilities in this sense.
Yes, precisely.
Yeah, okay, so you have this set of numbers, and then you have an event.
Yeah, so this event means that this set is biased in some way.
Yeah, but why? So now you have to define the probability of the event.
Yeah, that's
having the distribution having this conditional distribution of each second level. So that's exactly what my point. So can you give it's very natural definition, and probably it should be considered for a long time. But so how will you define this? So, no, actually there are different natural ways.
Can we add some additional requirements about the algebra of measurable sets?
Well, measurable as finite, so everything is measurable. Or you want to?
Not. And maybe we should just formally declare that some things are not measurable. just to have the ability to define it. Maybe, I think that if we want to define the probability in this case, it would be rather reasonable to add some requirement about...
So you want this set to be measurable and this set to be not measurable?
Yes.
Yeah, but what in a sense you can do this, but let me now say what is the natural suggestion. So you define something which is called max probability or upper probability. I don't know what should be the right name. Volodya Vovk probably used the name upper probability, but I don't know, maybe somebody considers it under a different name. So the idea is that we want to have, we consider some event E. Let's take all the probability distribution which have this correct values of conditional probabilities. And let's take the maximum of probability of all events. So it's somehow a worst case. If E is something undesirable, we just think that the environment wants to make this happen. And the other thing, we can consider a probabilistic game, like in Arthur Merlin game. So imagine that we start here, and then at this point we have a random choice, and at this point our enemy wants who wants to obtain E, make whatever he wants. So the maximal probability that he can achieve in this game is just, of course, more or less for evident reasons the same value. And so this is a kind of I think that's a kind of correct counterpart for the notion of probability for this strange, I would say, this online. So we discussed with, so this is the result of discussion with different people, with Kolya Vereshchagin, with Volodya Vovk and Lyosha Chernov. But none of us knows the right name. Also, it was considered somehow in different context by Markus Hutter, who used some very strange name which I forgot. Okay. But what I want to say is that then, starting with this point, you can derive a lot of things related to standard algorithmic information theory. So just let me give a few examples, and then I stop. So, for example, you can try to define what is complexity. So usually you can consider the complexity of C1 bits C1 Cn just as the length of the shortest program that generates them. And now you can try to consider the complexity of bits C1 Cn in the middle of the sequence. So you have this x, just some strings or some messages x1, xn, and you want to know how difficult is to produce these bits in this context. So what is the natural definition? It's a length of the shortest program which does what?
Reads x1, outputs c7.
Yeah.
Then it is given.
Yeah, of course. A program is x1 is given, and then the program should produce c1. And then x2 is given, and program should produce c2, and so on. And this is not what is strange. This is not reducible to any classical Kolmogorov complexity. It's somehow in between. So we can consider just this new complexity is of course smaller than the complexity of the complexity of bits, because if you can produce the bits without x, you can do it with x's. And so it's bigger. This is bigger. But also there is an evident lower bound for the complexity. Which one?
Conditional with the condition of all x's.
Conditional of all c when all x's are given. So, and it's clear why it's why it's only a lower bound. because here you are allowed to use all x1, xn to compute this. And here you should do it online. You are given only one, and you get to produce. You have to produce one. So this is what is called complexity. If you know what is called a priori probability, you have just a probabilistic machine that normally you have a probabilistic machine without any input, but with internal random number generator, as Harry explained us today. You can even buy this machine. And then it produces a sequence of bits. And for each string, for each values of this bit, you can compute the probability that this bit really appears. So exactly you can do the same for this, but in this case you do have inputs. You put x1 and you get c1, you put x2 and you get c2. So the notion of a priori probability has a very natural extension here. Also, if you know what is the Martin-Löf definition of randomness, it's just a random sequence is a sequence which does not belong to any effectively null set. And of course here you can define very natural the notion of effectively online null set, so to say. And so you can say what means that the sequence of bits with C1 infinite sequence when these bits are really random with respect to this environment, online random with respect to this environment. So the claim is that a lot of things which you can do for classical algorithmic information theory can be in a very natural way, can be transformed into notions here. So then the natural question is whether it's just to try this and to find things which are difficult. And for example, one of the things which could be interesting, and I don't know the answer, but maybe you can think about this and find it as I know how difficult it is. So imagine there are very famous relation between prefix complexity and a priori probability. So prefix complexity is minus logarithm of a priori probability, whatever it means. Just there is probably one of the most important things. But it's not clear whether it remains true here. Even the definition of prefix complexity is not very clear because there are different definitions, and normally you prove that they are equivalent just by this theorem. So if you don't know the theorem, the definitions became not clear why they're equivalent or not. So this is the question. Also, it's interesting how to define, for example, monotone complexity in this case. And so what can be proved for this? And also this is somehow related to other thing which is rather interesting. There is a universal test of randomness. They have a very strange history. So there was a paper of Leonid Levin which is called Universal Uniform Test of Randomness, which was written in 1975 or something like this. And nobody really understood the value of this paper. Only very advanced people like Gach and partially Vyugin claim that they understand what is there. And indeed they sometimes even manage to explain what is there, but it was somehow not related to anything. And recently, just 2 years ago, or 3 years ago, there was another line of research in kind of learning theory, and there was another story which I just want to say this. And then recently Vovk found that there are more or less the same argument, and they may use the same argument that was essentially found by Levin 30 years ago. So maybe, I don't know, if we will have probably we'll have a Kolmogorov seminar, for example, on 10th of September. One of the possibilities that I'll try to explain this in detail. Of course, it's impossible to do this now. But so there is a kind of what I wanted to say, that there is a kind of probability, algorithmic probability theory and algorithmic information theory, which is first rather natural, second has some non-trivial, at least for me, non-trivial questions which deserve investigation. But many things are indeed working, and many relations which we have usually still are valid and can be used as a tool in this investigation. So this is a kind of advertisement for thinking about this. And so that's all.
Yeah, you run out of batteries. I'm sorry.
Yeah. So there is no reason of making an applause. It will not be recorded.
No, there are questions.
Yeah. Okay.
So how does it relate? Does it relate in any way to interactive protocols or something?
Just this is the probability which is used in Arthur Merlin games. So you construct
the same thing.
No, they don't. They have very specific distribution, but of course they consider exactly the same thing. And so there are also algorithmic questions. So imagine we have this tree. Also, there is another possibility. Oh, by the way, let me ask you another. Sorry, it's a cheating, but let me as a kind of answer to your question, say something. So you know Martin theorem, determinant theorem. So we have a Borel game. So there are two players. One is going. They alternate, and then after the infinite time, somebody decides who will the winner. And you know that there is, probably you heard that there is a very famous Martin deterministic theorem, that if we have a rule is Borel set, then either A or B has a winning strategy. Now imagine that we have a probabilistic game. So like A plays, makes the move, then B makes the move, and then coin makes the move. And then again A, B, and coin, and so on. And again we have a rule, but now the rule depends not only on the moves, but also on the coin tosses.
Yeah, but a coin toss is also a player who just has some very simple probabilistic strategies.
Yeah, sure, but it not only has it, but it's obliged to use it.
Yeah. I mean,
so, but let me make a formal statement. Hypothesis, which looks natural, that for such a game, there exists some number p with the following property. So if p prime is smaller than p, for each p prime which is smaller than p prime bigger than p, B can guarantee the probability at most P to P double prime. So there again is some kind of determinacy in a natural way. And I don't know. I asked Gurevich about this theorem, and he asked, I think, Blas or somebody, and they both told me that they are not the experts, but they didn't hear anything about this. So if anybody knows this, or knows how to prove this, or knows anybody who may know how to prove this, I think it's very natural question. So since you asked about the connection between the games and previously considered question, so what Arthur Merlin class is one thing, and Borel deterministic theorem is the other. Okay, sorry for...
No, that's...
But just who knows the proof of Martin theorem about Borel determinism? Are there anybody, somebody in the room who knows the proof? Okay, so
So tomorrow we start again at 9:30 with Lev Beklenichev's talk about Gödel theorem for very weak system. But actually this should be also a tutorial because he will continue the day after tomorrow.
yeah. So and usually he explains very
well. And once I recall, who signed for lunch should take the ticket for it.
Now they should take and
now or tomorrow, but better now. Not.
But what has higher probability that you lose all the tickets?
Yeah.
Можно так и напечатать еще много до вечера, да? Ну, видимо, да. Окей. Я думаю, приходите к мы сейчас сожжем домой.
А что, вы все уже там у него работа.
Нет, с него что-то
Да, я
чего?
Нет, честно, про это нет. Нет.
А также
Да, мне кажется, у меня даже есть фишки. Я не знаю, вы сейчас знаете, кто вроде оно есть.
Ну, либо вы можете обладать, а может кто-то помочь. Помню, что вы посмотрели. Хорошо. Есть некоторые вопросы, которые
Нет, там не все могут.
Да, давай.
Более понятно.
Lunch for tomorrow. Then I will give the day tomorrow. Not at all. So have you found that? Yes, repent.
That was easy.
But for you. But good for you that I have recorded the talk. You can sit now and listen to the talk.
вторая, что после прочтения человек может сказать, собраться
Вы сами ничего не практически. Вот жизнь через другой. Врачи с другими можно читать уже все.
Нет, не должна быть такая, что читать другие, нет, другие хорошие.
А что, кстати, да? Познавали программу такой. У нас по результатам
нет, в этом программе какой-то эффективности. Это такие
ну, риск называется так, примерно состоит в том, что
нет, ну я старался,
Это необычно.
да, я хотел сказать, что
Вроде вид распознавания букв.
Да, это было бы
Хорошая, известная тема. Вроде вид распознавания. Наука есть эта тема. Печатных букв, ну,
Нет, печатных, но
спрашивается, почему нет действующей open source программы, основанной на науке? Почему у нас все есть? Компиляторы есть, там то есть, все есть. А вот этим нет. Если наука есть, почему нет
Вообще называется subscript.
Можно потому что есть
много сложных разных вещей, с которыми...
Или нет, самый главный критик, там где-то все равно свалит.